The next thing we're going to look at is RAM. But before we look at RAM, let us explain why we need it. So it says here, one way to measure the efficiency of an algorithm is to implement it using a programming language like Java. So you implement the algorithm as a method, and then you will use a method like current time millis, which will return to you the current time. So you're going to call this method once before you start running your procedure. It will tell you the current time, and then call it one more time after the procedure has finished, and then take the difference. The difference will tell you how much time the algorithm takes to execute. Now you can run this for different size of data. So you can vary the input size, and then you can plot a kind of graph. Okay, so for example, when the input size is 50, the algorithm takes like this 2000 milliseconds. Okay, when it is 100, it takes like 9000 milliseconds, and so on. So you can plot and see how the algorithm performs with respect to input. It looks here like you are forming a kind of quadratic graph. Okay, however, this method of implementing an algorithm and then checking how it performs on a particular computer has many problems. I list some of the problems here. Number one is that it is necessary to implement the algorithm before you can actually evaluate its efficiency. And sometimes it may be difficult to implement the algorithm. So this is issue number one. You have to implement it to be able to analyze it. The second problem is that no matter how you tried, you cannot check your algorithm against all different input sizes. You can only use some sample inputs. So you cannot guarantee that this algorithm will be as efficient as you thought by just taking some few samples. This is what the second point is saying. The result may not be indicative of the running time on other inputs which you didn't include in your experiment. For example, here, if you look at the graph, we only check until 100. You didn't check until 200 or 2000 or 3 million. We don't know how this graph may change. Maybe it will go steeper or it will go lower, and so on. We don't know because we only check until 100. So this is problem number two. But perhaps an even more problem is this one, number three. It said the result that you get actually depends on many other factors, not just your algorithm. Such factors could include the programming language used to implement your algorithm. We all know that some languages are faster than others. For example, when you compile a C code, your code is going to be compiled directly into a machine language, and that means the compiled code is much likely to be faster. It's more likely to be faster than if that code was compiled using Java, because Java doesn't compile into a machine code. It compiles into a byte code, and that byte code has to be converted by the runtime system into machine code before it can actually be executed. So you'll see that the the result that you're gonna get, probably if you run your algorithm using C, may be different than what you will see if you run it, if you implement it in Java and then run it. Okay, so it could depend on, it could be showing you the efficiency of the programming language used rather than the efficiency of your algorithm. Another issue is that compilers normally do some optimization. When you write your code and you compile it to execute it, compilers normally add some optimization to make sure the code runs more efficiently. So maybe it is the optimized code that was added by the compiler that is giving you good results, not the original algorithm that you designed. Okay. Another problem is that it could actually be the computer that is fast. If you run the same program that you implemented on another computer that is slower or that has less memory, you may get a different result. So these are all issues that will arise if you try to measure the efficiency of an algorithm by implementing it and then executing it. Okay? We don't do it like that. So in order to compare two algorithms based on this approach, the same hardware and software environment must be used. So clearly this is not a good way to test the running time of algorithms. So here it says to avoid these problems, this method of analyzing algorithms is not used by computer scientists. Instead, a theoretical method that analyzes the actual operations of the algorithm relative to its input is generally used. The theoretical method uses a high-level description of the algorithm using pseudocode. So we don't do implementation. We try to analyze it from the pseudocode itself. 2, it characterizes the running time as a function of the input size n. So we're going to assume the input size to be a variable n. And therefore there is no issue of saying you only tested it with n equal to 10 or n equal to 5. No. Our analysis is based on assuming the input size to be variable. So it means it covers any size, not specific input sizes. Alright? 3, it takes into account, this is basically what I just said. And therefore it takes into account all possible input sizes. Since n is a variable, it takes into account all possible input. Number 4, which is probably the most important, is that this theoretical method allows us to evaluate the speed of an algorithm independent of the hardware and software environment. However, to apply this theoretical method, we still need a model of a computer that works very similar to a normal computer. And that is where the RAM comes in. So we call such a computer model RAM. RAM meaning random access machine. And we're going to describe the nature of this fictional computer in the next slide. So we're going to assume RAM has a single CPU and it has unbounded amount of memory. So the memory is limitless, but it has single CPU. Second, the basic types that this RAM can manipulate, we're going to assume them to be just simple integers and simple floating point numbers. Okay, so these are the basic types for our RAM. It can manipulate integers, it can manipulate floating point numbers. What are the basic steps in the RAM model? Basically, operations involving basic types. So this could be addition, subtraction, comparison, and so on. Load or store, basically meaning assignment, assigning values to variables, and arithmetic and logical operations. Okay, so plus, minus, slash, times, greater, less than, equal, and so on. We're going to assume that our RAM can execute all of this. Okay. We're also going to assume that our RAM can execute branch operations. So things like if, else if, and so on. So conditional branch as well as jump. It can also call a subroutine. So for example, from within the reverse method, we can call swap. Finally, we're going to assume that our RAM execute these basic steps in constant time. It takes a constant time to do addition. Another constant time, not necessarily the same as addition, but a constant time to do multiplication. A constant time to call a subroutine. So the idea is, if you do addition and it costs 5, next time you do addition it's going to cost the same 5. Multiplication may cost 10, but each time you do multiplication you're going to assume it costs 10. This is the idea. So we're going to assume that all basic operations are done in constant time. Good. So with this idea in mind, we're going to try and take example to see how to analyze an algorithm. So this is our first example. You recall our mystery 1 algorithm, which was actually a find max procedure. It takes an array A and it returns the maximum element in that array. So the question is, if you are to analyze the efficiency of this algorithm, assuming it will run on our RAM computer, how are you going to do it? So what we normally do is we draw a table. The table will have 2 columns, one for the cost of each operation. So each statement here, you identify the cost and how many times you're going to do it. So based on this table now, you come up with a running time function that depends on the input size. Okay, so let's go one by one. Here, the first line says key becomes A at 1, or assign the first element in the array to the variable key. Well, assignment is a basic operation, so we're going to assume it has a constant time. It costs a constant time. Call it C1. Okay, and obviously this statement is going to be executed only one time, so the number of times here is going to be 1. Okay, so we have C1 as the cost of doing assignment, and 1 is the number of times we are doing the assignment. It's only one time. Next, we have a loop. Now, if you recall the nature of loops, they actually involve 3 things: initialization, comparison, then go and do the body. After that, we do the increment. So for this first line, there are 3 things we're going to be doing. But actually, initialization is done only once. It is the comparison really that's going to be repeated many times, and also the increment. So each time we have to check, have we reached A dot length? Okay, I mean, have we gone beyond A dot length? Because if we have gone beyond, we're going to stop the loop. But if your I is less than or equal to A dot length, you're going to repeat the loop. Okay, so the question is, these operations of comparison and increment, they are both constants. So obviously, if you add two constants, you're going to get a constant. So the cost of doing this line is constant. So let's call that constant C2. But the question is, how many times are we going to do this? Especially the comparison and the increment. How many times are we going to do it? Now the comparison particularly will always, now this is very important, to know how many times you will put for the loop, you need to look at the body of the loop. How many times the body of the loop will execute. Whatever number you get, add 1 to it to get the number of times that the condition of the loop will be executed. Okay, why? Because there will always be one more comparison which will be false that will allow you to exit the loop. So that comparison, because it is false, we don't enter the loop. Okay, so basically then the number of times you execute the heading of the loop is always 1 plus the number of times you execute the body of the loop. So I advise that the first thing you do is find out how many times are you going to execute the body. If you can do that, then just add 1 for the number of times you will execute the heading of the loop. Because the heading of the loop will always execute 1 more time, which will be false. The rest of the time it will be true. If it is true, enter the loop. True, enter the loop. True, enter the loop, and so on. And then finally it will be false, exit the loop. Okay, so the comparison will always be 1 more time than the number of times the body will be executed. Now if you look at this loop, it starts from 2 until the length of the array. Let's say the length of the array is 5. Okay, so the body will run 2, 3, 4, 5. This is basically 4 times. Alright, so if you assume that the size of array is n, then the body will execute n minus 1 times. But the heading of the loop here will execute n times. Okay, this is the idea. If we were starting from 1, then obviously the body will execute n times. So in that case, you will say the heading will execute n plus 1 times. Okay, so this is how to do it. Always look at how, find out how many times the body will execute first. If you can do that, then you will know how many times the heading of the loop will execute. So we're going to say here that the cost of the list statement number 2 is constant, obviously, but the number of times is n. Alright, what about this if? So this if, we only do it if we enter the loop. And we said we're going to enter the loop n minus 1 times. So it's going to be another constant C3, but this time the number of times is n minus 1. Okay, now here comes the tricky part. How many times are we going to execute this assignment? Key becomes A at I. Here you have to be careful because this assignment will only be executed if this condition of the if statement is true. In other words, if we find another value that is greater than the current maximum, only then should you update the current maximum to that new element. So here really we don't know how many times we are going to find a value that is greater than the current maximum. We don't know. But we know, we have an idea of a range. It's going to range from 0 until n minus 1. Why? Because if this first value that we assign is the biggest, then we will never do this assignment. We will never change it. So in that case, this assignment will execute 0 times. Okay, the other scenario is, suppose the elements are sorted in increasing order. Then it means, and you have initialized your first maximum, you initialize your maximum with the first element. Now obviously each time you go to the next element is going to be bigger than the current max. So in that case we have to do this assignment equal to the number of times you execute the body of the for loop. So it's going to range from 0 to n minus 1, but we don't know exactly the number of times. Now if we don't know the number of times, what we do is we use a variable. We will say, okay, it will execute some number of times, call it t. If there is more than one similar case in your algorithm, then you can call them t1, t2, t3, and so on. So we're going to say this assignment will execute. The cost is constant, of course. It's a simple assignment. So C4, but number of times we don't know, so we use the variable t. And here we are saying t will vary from 0 until possibly n minus 1. It can be any one value from this range. We don't know exactly. It depends on the arrangement of the values inside the array. Okay, the last statement is a simple return, which is constant, and like the initial assignment, is going to be executed only one time. So we say constant C5, and the number of times is 1. So now that we have found the cost of each statement in this algorithm, we now define our running time function as a function of n. So we say Tn, the running time function is normally represented as capital T. And by the way, the n here is, if you like, is a reserved word. You don't use it as a variable, for example, because n in an algorithm simply means the input size. The input size is n. So don't use n for anything else other than the input size. And this running time function, we are defining it to be a function of n. Okay, so our Tn is going to be C1 times 1, which is C1, plus C2 times n, so C2n, plus C3 times n minus 1, plus C4 times t, plus C5. So obviously we can collect the lag terms and try to see if we can simplify the running time function. There are two terms involving n, C2n, C3n. So if you factor out the n, you will have C2 plus C3. And then you have terms that involve the variable t, which is the C4t. And then the terms that are constant, we're going to have C1 here. There's also C5. There's also minus C3, because C3 times minus 1 is minus C3. So we can collect those together and put them like this. Okay? This is the best we can do at the moment. But we can actually try to see what is the best scenario in terms of running time for this algorithm, and what is the worst case scenario. The best scenario is if the first element in the array is actually the maximum element. Okay, so you assign it only one time and you never have to do it again, because each time you reach another key is not going to be greater than that one, so you will never have to do this. In other words, the t here is going to be 0. So if t is 0, then we can in fact simplify our running time by eliminating this term, because if t is 0, c4 times 0 is 0. So your running time is simply the remaining terms, c2 plus c3n plus c1 plus c5 plus c3. And this we can now simplify, because of course if you add 2 or more constants, you're going to get another constant. So we can represent this simply as an plus b, where a is the addition of these 2 constants and b is the summation of these 3 constants. So our running time in the best scenario is an plus b as a function of n. Clearly this is a linear equation in terms of n. Okay. What about the worst scenario? The worst scenario is if the elements in the array are in increasing order, so that each time in this loop, the next element you're going to encounter is going to be bigger than your previous maximum. So you have to enter the loop to actually update the maximum. Alright? So in that case, your t here will actually be n minus 1. Okay? So if it's n minus 1, then going back to the original equation, here now we're going to have c4 times n minus 1. So we have another term with n, and when you simplify, you're going to have c3 plus c2 plus c3 plus c4n plus this other term. So again, you will have another linear equation, where in this case a is the summation of these 3 constants and b is the summation of these 4 constants. Okay, so either way you are getting a linear representation. Okay, let us now take our second example of analyzing the efficiency of algorithms. This second example is more interesting actually than the first one, because it's an algorithm that you already know, one of the sorting algorithms. It is also more interesting because it has a nested loop. So this time we need to be a little more careful how to count the number of operations. So here is the statement of the problem. Given the input as a sequence of numbers, a1, a2, and so on until an, we want the output to be a permutation or reordering of these numbers into a1 prime, a2 prime, and so on until an prime, where a1 prime is less than or equal to a2 prime, that is less than or equal to a3 prime, and so on until the last one. In other words, the elements are sorted in increasing order. This is the expected output. And this is the algorithm for doing that. Insertion sort. Let's go through the algorithm. It takes an array, obviously, as input. And if you recall how insertion sort works, basically we conceptually divide the array into 2 portions. The left portion we assume is sorted, initially just 1 element, and the rest are unsorted. Then we're going to take the next one and insert it in the correct place in the sorted list, so that the sorted list now will have 2 elements and the rest are not sorted. And then we again take the next element in the unsorted list and try to insert it in the sorted list. So the sorted list will be growing while the unsorted list will be decreasing, actually until the unsorted list become empty. This is the idea. So, and this is precisely what this pseudo code is trying to do. You see, it starts a loop for j from 2 to a dot length. Why from 2? Because we are going to assume, as I just said initially, the sorted list will have the element at 1. The first element, since it is the only one in the left hand side, it will be sorted automatically. So we only need to worry with the rest of the elements, number 2, number 3, number 4, and so on, until the length n. So that's why the loop is starting from 2. For j from 2 until a dot length, what do? Take the element at j, save it as key, okay, and then, as the comment here says, insert that element into the sorted sequence. The sorted sequence actually is from 1 until j minus 1. So when j is 2, of course j minus 1 is 1. So you just have from 1 to 1, which is just one element. But if j is, let's say 5, so j minus 1 will be 4. So the sorted list will be from 1 to 4, like that. So we want to insert this element at j in the correct place in the sorted list. So to do that, we need another loop, because we're going to go through all the elements in the sorted part until we either reach the beginning of the array. So this is basically how the algorithm works. It says while I is greater than 0, meaning as long as there are more elements in the sorted part, because of course the sorted part, the indexing starts from 1, so 1 until j minus 1. So as long as I is greater than 0 means it is within that range. Once it becomes 0, it means we are now outside the array, so the loop should stop. The element at I is greater than key, it means we have not yet found the correct place to insert our key. This element is still bigger. So what we do is we shift this element AI to the right by saying A at I plus 1 becomes AI. Okay, so we are shifting AI to go one step to the right. Then update the I to becomes I minus 1. Okay, so we're going to go to the next element in the sorted list, and then repeat the loop. Okay, so as long as we have not reached the end of the sorted list, and as long as the element at I is greater than key, we have to keep repeating. Just shift that element AI to the right, and then decrement your I and repeat. So this loop will end either because we have reached the end, meaning the key that we're going to insert is actually going to be the first element in the array, or we have found the right place to do the insertion, somewhere in between. Okay, so how do we do the insertion? We're going to simply say A at I plus 1 becomes a key. Why I plus 1? Because if you recall what we said, the control variable for a loop will retain the last value that is assigned to it after the loop. So if we continue to shift to the right, the last value assigned to I is 0. This is why the loop stops, because I is equal to 0, the loop will stop. But we know from our convention that our array actually starts from 1. The indexing starts from 1. And therefore we have to say A at I plus 1 becomes key. Similarly, even if we have found a correct place to do the insertion, okay, so it happens that now a at I is not greater than key. Still, you see we have decreased I by 1. But actually we want to do the insertion at I. Therefore, we have to say insert this key at I plus 1. Actually, it is more clearer if we take an example to show how this algorithm works. So in the next slide, I'm going to show you an example with a sequence of numbers so that you can clearly understand what the algorithm is doing. So let us say we start with an array of 6 elements, as you can see here: 5, 2, 4, 6, 1, and 3. So as I said initially, we're going to assume the sorted part is just the one element 5. And now we're going to go through the rest of the elements in the unsorted part one by one. So each iteration of the outer loop, the for loop, will take one element here and try to insert it in the sorted part. Now here, as you can see, 2 is definitely, or rather the element at I is definitely greater than our 2. So what we do is we shift it to the right. So 5 will come here, and we try to now decrement I by 1, and you can see that we will reach the end of the array, and therefore we will have to put the 2 at the beginning. So the result you will end up with is, as you can see here in the B part, 2 is now at the beginning of the array, followed by 5. Next, we go back and pick the next value of j, which is 3. So the concerned element here is 4. So again, the idea is to insert this 4 in the correct place in this sorted list. And that's what the inner loop will do. Okay, so we start by checking, is 5 greater than 4? Yes, it is. So move it to the right. Okay, and then decrement your I to 2. So again you ask, is 2 greater than 4? Definitely not. So this is the right place to do the insertion. And therefore we're going to insert the 4 here. So this is the result. As you can see in the C part, we now have 2, 4, 5. Next, we take 6. So the new value of j is 4, and the element is 6. Now 5 is not greater than 6. So in fact 6 is in the correct place. We don't have to do any shifting. Okay, so just keep the 6 where it is. Assign it to the same place. Right. Next, we make j to be equal to 5, so that the element we're going to try to insert in the sorted list is 1. Now, as you can see here, we have to shift all the elements in the sorted list to the right by 1. Okay, 6 will go to the right, 5 will go to the right, 4 will go to the right, and so also 2. So that the 1 will end up being in position 1. Okay, this is what you are seeing here. 1 has come here. And the final step is for j equal to 6, which is the length of the array. We pick the element 3 and try to insert it in the correct place. It is going to end up here between 2 and 4. So the final answer is, as you can see here. Now, one thing to note is, although we are sure the outer loop will run from 2 until n, where n is the length of the array, we are not sure how many times the inner loop will run. It it all depends on the arrangement of the elements inside the array. See here, for 2, we only need to go through the inner loop one time to find the correct location for 2. Similarly here for 4, we only need to shift one place, so the inner loop will run one time. Here the inner loop doesn't have to run at all because 6 was already in its correct place. But what about here? 1. We have to shift 1, 2, 3, 4 times before we can find the correct place for 1. Alright, so the point is, whereas we know how many times the outer loop will execute, it will execute from 2 to the length of the array, we don't really know how many times the inner loop will execute. It depends on the arrangement of the elements in the original array A. Okay, this is very important to take note when we come to the analysis part. Now, before we look at the analysis, let us make sure that the algorithm is actually correct. So, correctness of insertion sort. One way to prove the correctness of an algorithm is to use what is called loop invariant. This is probably a new concept for you, as I doubt if you will have done it in the discrete structure course. But it's a very important and very common way to prove the correctness of an algorithm. We're going to see how it works in this example. So first of all, what is a loop invariant? A loop invariant is a property of a loop that is true before and immediately after each iteration of that loop. Alright, it is also a property that will allow you to actually prove the correctness of the algorithm. To prove that an algorithm is correct, we must show 3 things about the loop invariant. So first of all, we have to identify the loop invariant. What loop invariant can we see in a particular algorithm? So having identified, we now need to show the following. 1, which is called initialization. We need to show that the loop invariant is true prior to the first iteration of the loop. So even before the loop starts, the loop invariant should be true. This is step number 1. Step number 2 is called maintenance. That the loop invariant is true before each iteration of the loop, and it remains true before the next iteration. Okay, so it's going to be true before and after each iteration, basically. And finally, the termination part. We need to show that the loop invariant is true after the last iteration. Okay, right. So let's see what we can identify in this insertion sort as the loop invariant. It says here that the loop invariant that we can use to show the correctness of insertion sort is this: that at the start of each iteration of the for loop, so this is the outer loop, the sub-array A from 1 to j minus 1 contains the original elements, so no element is removed, but they are sorted. So this is the loop invariant. That at the start of each iteration, the elements, if you like, in the sorted part of the list will contain the original elements which were not sorted, but now they're going to be sorted. To show you this practically, let's go back to the description where we saw how the insertion sort works. You see, when j is 2, so j minus 1 is going to be 1. So the element from 1 to 1 obviously is just this 5. Okay? It contains the only number that is in this position, and since it's the only number, it is already sorted. Okay, what about when j is 3? So we are saying this part from 1 to j minus 1, meaning from 1 to 2, contains the original elements. Okay, the original elements were 5 and 2, but now we have them in sorted order. Okay, when j is 4, so when j is 4, again we are saying the elements from 1 to 3 contains the original element. The original elements are 5, 2, and 4. The only thing is that now they are sorted, 2, 4, and 5, and so on like that. So here you can see 2, 4, 5, 6 are the same as the original elements, 5, 2, 4, 6, only that now they are sorted, and so on and so forth. So this is our loop invariant. Now we need to show that the loop invariant is true. Basically, we're going to prove the three properties. Initialization is true, maintenance is true, and the loop invariant is still true at the termination point. Okay, so let's try and do that. So again, I repeat, the loop invariant is at the start of each iteration of the for loop, the subarray from 1 to j minus 1 contains the original elements but in sorted order. So is this true initially? Is this true after each iteration? And is it true at the end? If we can show this tree, it means definitely our algorithm is working correctly. Okay, let's take the proof. Now, initialization, it says here that just before the first iteration, we know that j starts at 2, and therefore the subarray from 1 to j minus 1 actually contains a single element, the element at 1. Obviously, since this is a single element, it is the element that is originally in the array, and it is also sorted trivially because one element is already sorted. So it means the initialization is true, and if the loop invariant is true before even the first iteration. Okay. Now, for the maintenance, we notice that the loop basically in each iteration is only shifting the elements to the right until we find the correct place to put the aj. So you say each iteration maintains loop invariant by moving aj minus 1, a at j minus 2, a at j minus 3, and so on by one position to the right until the proper position for the key aj is found. At that point, the key is placed in its position. So clearly, no elements is removed. It's the same elements as the original one. We are only shifting them to the right to find the correct place to insert aj so that the sequence will be sorted. So clearly, the loop invariant will be maintained after each iteration. So what about the termination? At the end of the loop, j is going to be equal to n plus 1. Remember, the last value of your control variable will be retained after the loop exit. So now the loop is going to stop when j becomes n plus 1, because then it is not within the range of the array, so the loop will stop. Okay, just to remind you, the loop of the for loop goes from 2 until a dot length. So j will be taking values 2, 3, 4, and so on. When it is equal to a dot length, which is equal to n, the condition is still true, so it will execute the body, and then it will be incremented by 1. So j will be n plus 1. At that point, the condition here will be false, because then j will not be within the range 2 to a dot length. The final value of j will be n plus 1. So let us see what does that mean in terms of the loop invariant. If j is n plus 1, it means our subarray 1 to j minus 1 actually will be 1 to n. Okay, so because the last value of j is n plus 1, so if you subtract 1, basically you will have the entire array. And clearly the entire array will be sorted, because according to the loop invariant, all the elements from 1 to j minus 1 will be sorted. So it means the loop invariant is also true at the termination. And therefore our algorithm actually sorts all the elements of the array. And it does terminates, as we saw there. So it is correct. This is basically how to prove that an algorithm is correct using loop invariant. The difficult part is identifying the loop invariant itself. And usually the best way is to, as we saw in that sequence of figures, we need to show how the algorithm works as the control variable varies. And from that, we should be able to identify what remains true throughout the iteration. And we take that to be our loop invariant. Hopefully by the time we take a few more examples, you will understand this idea of using loop invariant to prove the correctness of an algorithm.